Today we're going to talk about transforming the logarithmic function. So just to be clear here, what we have to do, according to the Ministry of Education for Ontario, we have to determine through investigation using technology the parameters a, k, d, and c in these functions. But notice that in the expectation, which the Ministry of Education says you must learn, this is a base 10 right here. So according to the above expectation, we only need to look at base 10 transformations. So this is our new parent function. It's a base 10. We're going to check out these transformations on decimals on the next slide. We're going to do that. But first, let's just do a little predicting here. Which of these parameters, a, k, d, and c, these ones here, would raise or lower the parent graph, would be a vertical translation? Which one would bring it up or down between these four? Yes, it is C. That's one of the easier ones, the ones that lifts it up and down, because we've learned that for a few years now, so that one's not too hard. What parameter will change the asymptote? How so? So which one of these will change the asymptote? There's only one. It's the D value, and it will shift it left and right. So the K value, sometimes students think, oh, the K value, that's a horizontal compression or stretch. But because our parent graph has the vertical asymptote right along the y-axis at x equals 0, it's going straight down the y-axis. When you take that and you multiply it by anything, or you divide 0 by anything, you're still going to be at 0. So the K value doesn't affect the asymptote. What parameter will cause the parent graph to be reflected through the y-axis? That is reflected through the y-axis is a horizontal reflection. That's kind of being flipped sideways. That's your K value, and the negative K value will do that. And the last one we're going to talk about is how will an A value between 0 and 1 affect a parent graph? An A value between 0 and 1, what does that do? It's the same thing it did for a parabola. If you had a value at the front that was 1/2. What did it do for parabola? It's a vertical compression. So let's take a look at these using decimals. All right, let's look at these transformations here. So what you're seeing in red is the base 10 log function right here. And if we add on the parameter of A, that gives you your vertical stretch. Okay, now in a second, it's going to flip over because my A value becomes negative. There's your vertical reflection. And when your A value is in between 0 and 1, it's a vertical compression. So that's what your A value does. Let's set that back to its default of 1. So A is always an invisible 1. Now the K value, here's what the K value does. It's hard to see, but it is a horizontal compression stretch reflection. So it's reflected right now. It's reflected to the other side, thus the negative. Let's get it back over there. Imagine taking the blue curve and you're holding it, or you've got a barricade here on this side so it can't go any further, and you're pushing it this way with your hand or something. You're squeezing it in. That's, except your hand's way over there at infinity. That's the horizontal, I think it's a horizontal compression. So it looks a lot like a vertical stretch, and many functions do. It's hard to tell a vertical stretch and compression from a horizontal stretch and compression. But when you have the equation, you can tell because you look at the value. So when we have a K value that is in between 1 and 0, it's a horizontal stretch. Again, it looks like it could be something else, and we're going to explore that in a minute. Let's put it back to 1 because the K's default is 1. C value, its default is a 0, so we all know what happens with the C value. It's going up and down. And notice the asymptote. Now the asymptote is going up and down with it, right? But you can't tell that because it's infinite. So the asymptote might look like it's moving there, but really it's staying in the same spot. So the C value, that's old hat. Everybody knows what the C value is. Let's set that back to 0. And the D value, here's where we're going to see our asymptote moving. So I made this equation down here. I wrote x equals d. That gives us our dotted
our dotted red line, and there's the d value up here. So when I move this, it should move the s. It moves the asymptote as well. So the asymptote moves back and forth with the d value only because it's a horizontal translation, right or left. So those are all of the, let's turn them all on. Just, wow, this is crazy. Okay, so we've got all the transformations going on here, a, k, d, and c value, and that is what they all look like. They all do the same thing for the logarithmic function that they do for any other function that we've had.
All right, here we go. Let's graph our new parent function. Now, one thing you can do if you like is you can, instead of using f at x, you can change that to a y. Y equals log base 10 of x, like that. And that's because sometimes we're changing to exponential, and when we are converting to exponential, it's a little bit easier if I write this as, so in exponential, this is equivalent to, when you see an arrow like this, means equivalent to, my base is a 10, my exponent for this would be a y or f at x, and that will equal x. So that's just converting. So let's just start this new function by looking at some relationships we already know. We already know that 10 to the power of 0 is 1. So what I'm going to do is I'm going to use this format here. 10 to the power of 0 is 1. I'm going to get my x and my y from that format. So that if 10 to the power of 0 is 1, then that means the 1 is really, so the x spot goes there, the 1 is really the x and the exponent is the y. So that is a coordinate on our new graph, and that's equivalent to writing this log base 10 of 1 to the power of 0. Similarly, the next one below it is, let's change colors, log base 10 of 10 equals 1. And we're still getting used to this new notation, so it might be a little bit easier to think about it in this form, in exponential form, and then you can get your x and y values out of that form there. So that's giving us this coordinate that's on the graph, 10, 1 is on the graph, and continuing on we have another one, 10 squared is 100, everybody knows that. Then that means this is the equivalent logarithmic form of the same problem. So we get this coordinate, 102 is on the graph. Not 2, 100, but 102. But 102 is too big to graph. So usually it's common to use the point 32 and 1.5. There is a special kind of graph paper called logarithmic graph paper, and I encourage you to look that up and see what it looks like. And it's because the graph, these x values get really big while our y values stay kind of small. So there's a special kind of graph paper you can use for that, although we won't. But 32, 1.5 is a common approximate point here. Let's get one more. We know, well, this didn't turn out very well with my formatting. This is supposed to be 1 over 10. It looks crazy. This is supposed to be 1 over 10. 10 to the negative 1 is 1 over 10, which is 0.1. So we, in logarithmic form, it would look like this. So here's our x value, and here's our y value. And we get a coordinate from that. What exponent could we raise? The last line here says, what exponent could we raise 10 to in order to get 0? So what I'm saying there is, well, I have it here, 10 to the power of what is 0? 10 to the power of what is 0? Do you have an answer for me? I hope not, because the answer is nothing. There's nothing that you can raise 10 to that will give you 0. Therefore, we have a vertical asymptote at x equals 0 because there is no value of x that will work here. So let's put all of these points on the graph. I already have my x and y axis on. I'm not going to try and get this 100 number on my x-axis, I already explained that, but I will try to get 32 on there. So I think I can count by 2s. on my x-axis. Here's my x-axis, I can't buy 2's. And on my y-axis, I've got lots of room there because my largest y value, looking at all our coordinates here, the largest y value I've got is a 2. So I can really spread these out and I can count by halves actually, but I'm just going to label every one. That my 1 is kind of messy there. Let me fix that. That should be a 1 and -1, -2, -3. And I'm just going to press pause and I'm going to write all my values on the x-axis. Okay, the next thing I'm going to put on is that vertical asymptote at x equals 0. So I'm just going to get my ruler and I'm going to put let me move it to the side a bit so you can see it a little bit better. It should be right on the axis, but it's hard for you to see it if I draw it right on the axis. Go a little bit to the side. There's my vertical asymptote. That is x equals 0. And now I'm going to put all those points. I'm going to use red for all the coordinates that we circled up above. I'm going to do that now. I'm going to press pause and put them on, and you should do the same. So press pause right now, and when you come back, you can check. Right, there we go. I just wanted to point out that one coordinate 32, 1.5, that's an approximate coordinate, right? 32, 1.5 is not exactly like 10 to the power up. We're not going to get 32 exactly, but it's a common kind of practice to use that number. Okay, so we've got our red dots here and my asymptote. I know I cannot cross a vertical asymptote. So I can sometimes cross a horizontal one, but never a vertical. So I'm going to connect my dots and I'm going to try, I'm going to start right on my x-axis and use this point and curve off to the right first. And an arrow there because it's still increasing and still continuing to infinity. And then down this way, I'm going to get really close to the, really close to the x-axis there. It shouldn't bump out, but not crossing it. So that is our new parent graph, f at x equals log base 10 of x. That's what that one looks like. But of course, our topic today is transformations. So we're going to take this parent graph, and you saw this on Desmos as well, but we're going to do transformations by hand as well. On the same grid, we're going to graph g at x and take a look at what we've got there. It's much more complicated. It's got a lot of transformations to do, but first we're going to find the x-intercept by subbing in y equals 0. So the x-intercept is always a really important part of any graph because it's a root, right? It's an important point always when we're looking for roots or zeros or solutions. So this is I have got one, this was on my parent graph, but I want to find the x-intercept of this graph here. And I'm going to find it algebraically. Think of this as y right here. Change that to a y, but we're going to sub in 0. So we're going to just do a little bit of algebra, bring the 1 over. Now to get rid of the negative in front of the word log, that's really a -1, but I'm going to divide both sides by a negative. Now, once you have just a log on one side, even though it's kind of big, but this is all bracketed together, so it goes together. We don't have anything like a plus 12 out here, or we got rid of this number. Once we have just a log on one side and a number on this side, now we can convert from log form to exponential form. So when you convert this to exponential form, what will it look like? Do you remember? Remember 10 is the base. 10 will be the base. What will be its exponent? The -1, and that's going to equal 2x plus 6. And 10 to the power of -1, of course, is 1/10. Now we're going to solve for x. So we're kind of back at a grade 9 question here. Subtract 6 from both sides and then divide both sides by 2. And we get approximately, the dot over the equal sign means approximately, -2.95. That means I have a coordinate. Now the question said find the x-intercept. That's what I just did. This is my x value. When I subbed in, remember I subbed in a y value of 0. So when y is 0, this is x, so this is my coordinate, -2.95 and 0. So I have my first coordinate for my new graph, -2.95 and 0. So we'll do that in a second. I want to get a few other coordinates before I start with this. Now that I have one, I'm just going to switch gears here and just talk about transformations. I'm not going to sub in. That's way too tedious to sub in to find values. I'm just going to use transformations here. So what are the transformations? Let's look first at that negative sign in front of the word log. That means we're going to have a vertical reflection. So this red one, I'm expecting my graph to be, if that was the only thing, it would look like this, right? It would just be a negative vertical reflection. We also have right here some brackets which need to be factored. The k value always has to be isolated from the x value. X has to be alone and k has to be alone. So when I factor that out, I get 2x plus 3 for this piece right here. So that tells me the 2 is going to be a horizontal compression of my parent graph, and the plus 3 is going to be a shift to the left of 3 units. It also, remember the d value is also the vertical asymptote, so that's really good. Actually, let's put that on right now before we go any further. I'm going to use light blue for this. Let's get that vertical asymptote on there at -3, because that really helps us to block in kind of our graph. So -3, it's hard to line up my ruler on my tablet here. This looks pretty good here. I hope it's going to show up okay. There's my asymptote going through x equals -3. That's my vertical asymptote, and that helps me with my kind of boundaries and things. Remember that way down here at the bottom, this x-intercept, -2, that's almost right at -3. So it's really, really close to my asymptote here. Let me just put a dot there. Of course, this isn't accurate. Really, this looks more like maybe -2.5 or something. But we need to be really, really close here to the asymptote. Okay, back up to our transformations. So we've got almost all of them done. We just have one left here, and that means that the red graph will be shifted down. So our graph should have all of these pieces in it. It should look like this when we're done. And for some of us, it's really hard to just graph with transformations. So to graph with transformations, you would take a coordinate, then you would apply all these transformations on it and let it land in its new spot. So we can do that. We can do that in our head, some of us, but others of us need to actually work out the coordinates. So we're going to do that. I just have to find some space for it here. All right, I'm going to write small here, but what I've done is at the top I've put just the basic main coordinates from our parent graph that we had from here. I just included them all here. And now you can decide the method that you prefer for graphing, and you have some good methods, and all of you should be really good at graphing transformations. It's the same thing that you've done with the sinusoidal graphs or the polynomial graphs. The transformations are the same. Everything is exactly the same. You just have different coordinates to do. So using these coordinates, you decide how you want to graph. And I'm not going to work them all out for you, but maybe I'll do a little kind of a getting you started here. So if you're using the method where you are, let's say, writing the coordinate equation. So the coordinate equation is you take your x value, you divide it by whatever your k is, and then you add or subtract your d value. For your y values, you multiply them by a, and then you add or subtract your c. So for the graph we are going to draw, we're going to take all of our x values and divide them by k, which is a 2. So I'm going to take all of these x values here, and I'm going to divide them all by a 2. And then I add or subtract d. In this case, it's over here, right? Plus 3, that's 3 to the left. So I'm going to subtract 3. For my y values, I'm going to multiply them by a. And my a value is just a -1, so just a negative in front of that. And then add or subtract c, so in this case subtract 1. So you're going to sub all of these points here, all these coordinates, you're going to sub them all into this coordinate equation here, and you will get a new graph. So you're going to press pause now, and you're going to figure out those coordinates. I also am going to do the same, and I'm going to draw my graph. So now is a great time to press pause and figure out the rest of your graph. Sorry, before I continue on, I realize that over here I have, this is not approximate, this is exact. I shouldn't have that dot on top of there. Just taking a look at that now because I'm going to graph this point and it is exactly right. This number is correct, it's not approximate. So that's my mistake back there, sorry. Now press pause and go ahead and put your dots on. So there's all my points and I labeled them with the correct value. Now I have to connect them, and it's kind of difficult when you first look at a logarithmic graph and you've got some dots and you think, how am I going to get a shape out of this? Well, remember that the shape that it needs to look like is what the red one looks like. It's got to have this kind of shape. It's got to be really close to the asymptote, and then it's going to curve out, in this case, to the right. And we have some changes, some horizontal compression. We know, remember, we have this vertical reflection here. So we know that it's got to be coming, instead of this one's increasing left to right, it's going up, up, up. Ours is reflection, ours is going to be coming down, down, down. And that matches with where our points are. We've got an asymptote right here, so we're going to start up really close to the asymptote, really close, then getting a little further away, and then we branch all the way off to the right here. So connect your dots with a smooth curve if you can, and that will be your transformed graph. So there we go. And as always, you can check, well, I didn't put an arrow, sorry, on the left. As always, you can check, you can substitute some numbers into your calculator and see if they work out right. Say, for example, you wanted to sub in this value here, 13 and 2.5. You go over to your equation, in for x, you put a 13, and then you work it out and you see if you get the right answer. It's a good way to check to make sure that your coordinates are right. Most calculators have a default setting. That's why you can check it. If you look at if you get your calculator, it won't show you a base 10, but your calculator almost guaranteed has an automatic base of 10. So the way you can check that, if this is your function, log base 10 of x, we want to see what the y values are. Now you already know what they are. You should already know what they are for these values right here. So 10 to the power of what is 10? That's what this part is asking right here. 10 to the power of what is 10? That's what I'm trying to calculate. So if you put this in your calculator, you don't type a log base, you don't take the base is already there. So you're just going to hit log 10, or maybe you have to hit the 10 first in the log, I don't know. But you should be getting a 1 right there. That should show up as a 1 on your calculator. If it's a base 10, it should be doing that. Try the 0.1. That, as you know, should be a -1. 32, we just did these on the graph. Put in a 32, you're getting about 1.5, and 3, 0.5. So if that's working out for you, then your calculator has a base of 10. On the test, the question will ask you to show your work. You get to use your calculator for your test, and if you have your calculator is a base of 10, just be able to show algebraically how you found your answer. But you can check with your calculators. And that's been the case for the whole year, right? Example 2. This one's about equivalent algebraic expressions involving logs and exponents. What am I talking about here? So you'll see. Use your calculator to find coordinates on the following 2 graphs, and we're going to sketch the graphs and we're going to explain our findings algebraically. First of all, look at the first chart. So using your calculator, this is nice, you just get to use your calculator here. You're going to put in first a 10 in for x. So first thing you'll do is 100 times 10. Then you need to find log of 100 times 1,000. So when you do that, the number goes in here, and you should get, see this green, you should get a 3. Next, I want you to sub in a 5. So right here, in for x goes a 5. 100 times 5, that's 500. And then log base 10 of that number, that's a 2.7. Sub in a 2, you should get 2.3. Sub in a 1, that's an easy one, that's a 2. 0.1 is also pretty straightforward there. You're getting a 1. And what happens when you sub in 0? Okay, try this on your calculator. What do you get for the 0? What is log base 10 of 0? I'm not sure exactly what your calculator will tell you, but what it's trying to tell you is undefined. Whatever, you might have an error there showing or something. Undefined. We'll try -1 now. That'll be a -100. You're going to find log base 10 of -100. Also undefined. Okay, so let's graph this here. Take a look at the values. So I haven't pre-drawn the axes in here. Where am I going to, these are my x values here. My highest is a 10. These ones don't even really count because they're not going to be on the graph. Where's my asymptote going to be? Remember, your asymptote is your d value. What's my d equal to here? I don't see a d, so it's a 0. So my vertical asymptote is going to be at x equals 0. And then all my x values are positive, which means I'm going to use a ruler in a sec, but it means I can put my y-axis somewhere over here because all my x values I'm going to be using here are all positive. So I don't need to put my y-axis down the middle. Now, what about the x-axis? Where am I going to put that one? Well, I've got, look at your y values. The y values are also all positive. So I'm going to draw my axes kind of so that I'm utilizing my space the best here. So let me put my y-axis right here. I am using a ruler, you can't tell. And I'll put my x-axis a little lower, but maybe about, maybe about here. You don't want to know how long it took me to just draw those lines. I had to keep erasing them, but yours was fast, I'm sure. I decided to count by interval of 1/2 on the x and the y-axis because I have lots of space and my numbers aren't very big. My next step is to put those points on. So I'm, for example, 10-3. Let's put 10-3 on there, right there. And I'm going to press pause and put the rest of these points on, including this vertical asymptote. And there's my black points and my vertical asymptote. I'm going to connect those points with a curve. And remember, you don't just stop at one of your coordinates because you stopped calculating them. For example, sometimes I'll see students that will hand in their work on a test or a quiz and they'll just go like that. That is not a log function. Characteristics of a log function, first of all, is that they'll go in one direction to infinity. So you need that there. And on the other side, they get really, really close to the asymptote, but they do continue going down or up, depending on which way they're going. So you can't just put your points on and stop, or you won't get a mark. That's not a logarithmic function. So here is what we have just graphed is log base 10 of 100x. So this is f of x. This had a k value of 100. So compared to our parent function, we have a horizontal compression by a factor of 100. So it really got pushed in there. That's why we were able to have an x-axis scale that was so easy to use. We didn't have to get up to 100 or anything on our x-axis scale because the numbers didn't turn out to be very big. Next chart, get out your calculator again. I'll switch colors. Okay, get out your calculator again. This time you're going to put in a 10. So what you're subbing into your calculator is 2 plus log base 10 of 10. So you probably have to do this first on your calculator. Log base 10 of 10, of course, is 1. So 2 plus 1, this is a 3. Now you do the 5, and you'll get a 2.7. 2, sub in a 2, and you get 2.3. Sub in a 1. This is a 2, sub in 0.1, you get 1, and sub in 0 here, and of course this is undefined, as is anything on the other side of 0. Anything on the other side of 0 is going to be undefined. So look at these numbers here. They're exactly the same. The same numbers that you put in the chart for y values. Here and here, they're exactly the same. But these equations, this is a horizontal compression of a factor of 100. This is the parent graph. and it probably makes more sense to take this 2 and move it over here to be plus 2 over here. This is just a C value of 2. It's been lifted up 2. So we go back to our question, which was equivalent algebraic expressions. These are turning out to be equivalent, even though they look so different. Again, horizontal compression by a factor of 100, and this is just the parent graph raised up 2. So how is this possible that we get the same? I'm not going to graph it again. It's the same graph. The D value here is another 0, so it would be the same vertical asymptote. How is it that we are getting exactly the same graph with so completely different looking algebraic expressions? So to explain this to you, I'm going to give you a bit of an advanced preview of one of our laws of logs. We have several laws. One of them is called the Quotient Law, and we need that law to help explain what is going on here. The Quotient Law, now this looks kind of bizarre to you right now, but I want you to think back to your quotient law of exponents. If I had m to the power of 7 divided by m to the power of 3, that would be m to the power of 7 minus 3. So we see subtraction and division kind of having corresponding features here. The same thing when we get to logs, because logs and exponents are really closely related. So when we have log base a and log base a of something else, but we're subtracting them, it's the same as dividing, putting them together as division. We're going to talk more about this when we get into logs, but we just kind of need to you need to be aware of that law right now so that we can move on to explaining what was happening on that previous graph, that we had those two graphs that should be so different, but they weren't. These were the two. This was our first one. This is our horizontal compression by a factor of 100. This was our parent graph with just a C value of 2. So they're equal. They turned out to be equal to each other. So what's going on there? Let's do the algebra to prove this. The first thing I want to do is take this log over here. I want the logs together. I want the logs on one side, kind of like this pattern up here, right? I want the logs together. Now when you look at this right here and this, I should be able to take these two logs and write them as 1. It's almost like you're factoring out the log base 10. You're not. That's not what you're doing, but it's maybe at this point it's easy enough for you to think of it like that. So these two both have a common log base 10. So I can rewrite them like this. That is going to look like 100x over x. So the log base 10 is just written once, and then I take my inputs here, my 100x and my x, and I put them over each other. Now, of course, you know that these will cancel out. They're parts of a monomial. So we're left with log base 10 of 100 equals 2. And that is, if I rewrite that in exponential form, my base is a 10. That's this one. My exponent is a 2, and that's a 100. So we have proven that this graph on the left equals this graph on the right because we got our left side to equal our right side. This line right here was enough to prove left side equals right side, but some of us still need to go into exponential form to see that. So when I converted it into exponential form, it was a little easier maybe to see that the left side was equal to the right side. So we used the quotient law of logs to prove that those two graphs are equal to each other. And we really do get more in depth with these logs later. But for now, all you need to know is that is one of the laws that you can use. So one last thing before we sign off here. If you are not given a base in a question in your homework like this one, there's no base there. If you have no visible base, that's because the default base is a 10. So you can write the 10 in if you want to, but you don't have to. It's either or is fine, because anytime we don't see there's no base given, we know now that it is an invisible base of 10. It's like if I said 3x, that's an invisible power of 1 there. You don't have to put the 1, we just understand that to be there now. Okay, that was kind of a complex lesson, getting a bit of a more understanding of logs and using transformations to learn more about logs. So good luck with your homework.